Hello folks, and we're back with a little bit more today on sources, grounds, and battery life. So we've defined what voltage is and what current is. So let's take a look at schematic symbols and some practicalities. DC sources. If we're going to look at a voltage source, usually these are denoted with a capital E. E for electromotive force. There's two symbols. Probably the more common is this one. And the plus and minus indicate the polarity, positive to negative. Sometimes you'll see them drawn as a circle with a plus and a minus inside. But this one is definitely the more common one that we'll see. As far as current sources are concerned, probably the most common is an arrow showing the direction of the current inside a circle. An older symbol that you still sometimes see is a pair of circles like this, sort of overlapping, and then they'll put the arrow next to it. So again, that's the one that we're going to be using mostly. And when we draw this, we're talking about an idealized source. So if I draw a voltage source symbol, this is, the sort of personification, the perfection of a voltage source. No matter what we hook up to it, we'll get the same voltage. So if I took a 9-volt battery out here and I hooked up, a light bulb, I'm just going to draw a little box. I could hook up a light bulb. I could hook up, a heating element, a little DC motor. I could hook up a block of cheese, right? It wouldn't make any difference. This thing would always produce 9 volts. That's the idealization. In reality, that's not really going to happen. There are physical limitations on this. And one of our goals as we move through is to come up with better and better models. Things that more accurately describe reality. And we find that we do this a lot. Now, a voltage source everybody's familiar with in terms of batteries. Right? That's an ideal constant voltage source. So these are also referred to as independent sources. We say they're independent because nothing really affects them. They're independent of any other voltage or current in the circuit. As you will see, there are also things called dependent sources, but we won't see those for a little while yet. Those are often used to model active devices like transistors. Now, when it comes to current sources, we don't really have something like that we can, go to the store and buy. We buy constant voltage sources, batteries, but we don't really buy constant current sources. So mostly we use current sources, again, as models for more complex devices like transistors, or sometimes it's possible to convert a voltage source into an equivalent current source to ease analysis. It's just a little technique that we'll use. So, sort of a flip, if you will, a duality. Okay. The other thing we will see a lot is a ground symbol. Just remember that ground is a common. That's all it is. It's a reference point. We have 3 symbols for ground. The first, and the one that you see most of the time, is this one. This is really an earth ground. In other words, that goes back to the same potential as the earth. If you look at an AC outlet, right, in North America anyway, you get something that looks like this. Almost looks like a smiley face. That right there, that's your earth ground. Okay. If you go outside your house, you'll probably see either a copper bar going into the ground, or they'll attach this to a water pipe, a cold water pipe, on a good solid earth ground. Well, not everything needs to be connected to Earth. I mean, there's safety reasons why we have that in your home electrical distribution system. But not everything needs to be connected to Earth, right? That's impractical in many cases. I mean, if your cell phone was connected to the Earth, it's not going to be very portable. So we have two other symbols for that. This is the first one. This is called a chassis ground. So it's a common, typically this would go back to the metal chassis of a device. And then we also have this sort of thing. This is a system ground, a signal ground as it's often referred to, and this is commonly used where we have to separate the common between, say, a digital system and an analog system. So we have a mixed signal system that's part digital, part analog, and we don't really want all the switching transients that are being caused by the digital system to sort of leak into the analog system because that creates noise. So we need to separate those out. So in our work, the vast majority of the time, we're going to be using the Earth symbol, even if the circuit doesn't really need to go back to Earth. Now, on a power supply, a constant voltage power supply that you would use in lab, very often you will see a set of leads on here. So you'll see a black lead and you'll see a red lead. So the color code basically is that the red is the plus and the black is the minus. It's not necessarily going back to true earth ground. There probably will be on here a green color-coded lead that is in fact true earth ground. So you don't have to hook this thing up to true earth. If you need to, you just get a little jumper that goes from here to here. You either do it directly here or on the circuit board. But that's only if you really need a true earth ground. Right? In lab, typically we don't need to do that. This thing can be floating, like I said, your cell phone, or imagine the electronics on, an airplane. That wouldn't be very practical. You have a 7-mile long piece of copper wire draping across the ground, right? That's not going to work too well. Okay, so that's what we're looking there. Now let's continue with our battery source. If we were to take our sort of, like I said, idealized battery, and we were to measure this voltage, that would never change. It would be a fixed value, whatever the voltage rating is of the 9-volt battery, a 6-volt battery, a 12-volt battery, and that would be like it forever. But real batteries don't do that. For example, consider the fact that we have D cells, C cells, AA cells, and AAA cells. All 4 of those are 1.5 volt batteries. They all produce 1.5 volts. So what's the difference? I mean, physically, yeah, the Ds are really big, the Cs are a little smaller, the As are fairly small, and the AAAs are quite a bit smaller. It all has to do with capacity. Batteries are energy storage devices. How much energy, right? Think back in terms of joules for energy. How much can they store? Well, partly that'll have to do with the physical size of it, and partly it has to do with the chemistry, a zinc carbon cell versus an alkaline cell. But physically, a D cell holds considerably more than a C, which holds more than a AA, which holds more than a AAA. But they're all 1.5 volts. You can, in fact, if you had a system that was using AA's, you could wire in D cells to it. It would work perfectly well, but it would last longer. It's, of course, physically larger and heavier, so you probably don't want D cells on a small portable device, right? Like a calculator. Be a pretty big calculator. Okay. Well, what if you hook up one of these batteries to something, whatever this something is, and we plot what happens to the voltage? Because we know eventually the battery just sort of dies out on us, right? So this is time. What we should get is 1.5 volts. And if this was an ideal battery, this thing would last forever. But that's not really what happens. Instead, what we will find is that it immediately starts to drop, it sort of levels off, and then suddenly it kind of dies seriously on you. That would be for a certain current draw. So if we said, for example, oh, this is drawing, just to throw a number out, 50 milliamps of current. Maybe this is 20 hours. Just to throw a number out there, okay? Now, if we change that current draw, like we crank up the current draw, so maybe now it's like double the size, it's like 100 milliamps. Well, this whole curve goes quicker. And what you'll see is that inflection point happened much sooner. Where does it occur? Well, I'll just throw a number down. I'll just say it's 10 hours. Now, if you multiply these things together, if you multiply the amount of time that you have and the current, you get a value. In the red case, right, we get 10 hours times 100 milliamps, or 0.1 amps if you prefer. So that works out to 1 amp hour. In the case of our blue device over here, it's 20 hours times 50 milliamps, or 0.05 amps. And that will also equal out to 1 amp hour. Now, for fairly narrow ranges of current, you're just going to get this constant. In this case, this is a 1 amp hour battery. That's the capacity of it. If we really push this, in other words, if we said, oh, does that mean if I put an amp in here, right, that this thing is going to last for 1 hour, if that's 1 amp? Well, probably not. This is not a perfectly linear, a nice constant that's going to occur. Generally speaking, if we try to draw a lot more current than the test value, that's going to shrink down. So we probably won't get an hour. Maybe we'll only get 45 minutes here. So in that case, we're getting 3/4 of an hour at 1 amp. So, that's 0.75 amp hours, or 750 milliamp hours. On the other hand, we could kind of go the other way with this. In other words, what if we're really sort of sipping, if you will, the current, like we're only drawing 10 milliamps. Now it's going to do something like this. It's off the charts! Okay, so if that's 10 milliamps, we might find that current starts to drop off, that inflection point starts to drop off at a considerably higher value, right? So, the blue one here, 50 milliamps at 20 hours, if this was perfectly linear, you'd say, well, that's, 1/5 the current, so this is going to be 5 times as much, 100. Now, it's probably going to be much, well, I don't know, maybe 120, 150 hours. It's going to be more than you expect. But for fairly narrow ranges, in other words, around the test value, you can treat this as a constant. So if we said, hey, what is the expected lifespan of this thing if we draw, 75 milliamps? In other words, halfway between these two, the 100 and the 50. Well, if you got about an amp hour each, you're going to get around an amp hour for this one, right? And you're going to end up with something in the middle. You're going to end up with, mid-teens. You're going to have around 15 hours for this guy. Okay? No, plus or minus. And of course, it varies from battery to battery. A fresh battery is going to be a little bit longer in time. You don't expect this thing to work out to the nearest minute because, after all, where exactly is this point of inflection? You know, do you want to count it at, here's my 1.5 volts, right? Do I want to count that at 1.2, 1.1 volts, 1 volt? You know, at what point do we say, you know, we're done, the battery is cooked? Depends a little bit on the application. And if you have an old-fashioned incandescent light bulb flashlight, well, what happens if it gets low? Well, the thing just gets dim. You know, it still works, it's just dim. On the other hand, some solid-state devices, if they have enough voltage, that's it. Nothing works. So it will depend on a bunch of things, okay? But that does give you an idea. So if you have, you know, an application, you're looking for some batteries, you can look at this amp-hour rating, and the higher it is, assuming they're being tested at the same current, the higher that number is, the longer that battery should last. And we can say in general things like alkaline cells are going to have a much higher amp-hour rating than an equivalent zinc carbon. So when we go from, you know, a D cell to a C cell to a AA to a AAA, that's really what we're seeing. You know, over here on a D cell, we're talking a few amp hours. You know, depending on the chemistry of the battery, you might be talking 5, 8 amp hours. You get down to AA's, and you know, you might be talking 800 milliamp hours, you know, 500 milliamp hours. It's just physically smaller. Even if it's the same chemistry, it doesn't have as much energy capacity. Okay? All right, so that kind of gives us an idea of you know, what we're looking at as far as sources. Now we want to hook stuff up to it, right? You know, I'm just drawing a battery with a box. What the heck is in the box? You know, we're not going to put a block of cheese in there unless you just want warm cheese. Okay, next time.